So the next question that we have to deal with, that we now can deal with, is how much energy would it take to launch a satellite? If we want to launch a satellite into orbit,
radius r.
how much energy would that take? Well, we get to review all this good stuff. E initial plus work non-conservative, which is how much work we're going to have to do, will be the final energy of our satellite. So we're going to use this to figure out, basically we can use this to figure out how much fuel we have to apply or how much fuel we have to give to a rocket so we can get this up to where the satellite can be in orbit. So we start off with this. Now, when you're launching a satellite, how much and what form of energy does it start with? You may say, oh, it starts at rest. It doesn't start at rest. Why not? Because in our universal view, this, by the way, is the Earth. Let's take a look at this thing. This is the Earth right here. So this is like the radius of the Earth here, our Earth. And we're going to do it from the equator. We're going to launch it from the equator. Why is that? Because the equator is moving the fastest of any part on the Earth. In fact, if you start on the equator, you get a major head start because you're moving at 1,000 miles per hour if you start from the equator. If you start from the North Pole, which would be right here in our view, you got a lot more work to do because it's not moving hardly fast at all. In fact, it's basically at rest if you launch from the North Pole. That's why we launch everything from Florida, because that's as close to the equator as we can get. It gives us a major head start. This V right here, it's about 1,000 miles an hour on the equator. So that gives us a major head start. You may say, oh, it's also got zero potential energy. Again, we got to be super careful. It doesn't have zero potential energy. This UG is going to be negative. Okay, it's going to start off, it's not an infinity. Remember, we have to use R, UG equals 0 and R equals infinity when we're doing these kinds of problems. So whenever you're not on the surface of the Earth, you pretty much always got to use universal gravitation rules. And so this is its total energy to start with. And ask yourself, will this total amount be positive or negative? Well, we just derived last time that it will be negative. It can't be positive. Otherwise, it would be at infinity with some speed. So the total energy of the satellite, if it's in orbit, cannot be positive. This is the work we're going to have to do to get it in orbit. By the way, this is before it's in orbit, so it even has less energy than if it were in orbit. So it'll be even lower than the energy in orbit. We got to do some work, and this is going to be what we found is its total energy when it's in orbit. Again, this only works for a satellite that's in orbit. We should emphasize that. Only works for a satellite in orbit. So that's your total energy of the satellite. Here's our initial kinetic energy, our initial gravitational potential energy of the system, and this is how much work we have to add. So let's go ahead and figure this out, what we need to do to get this work non-conservative. This is our kinetic energy initially, but notice I cannot use negative GMM, or sorry, I can't use, for this, you can't use the K of a satellite in orbit. You can't use this positive G at big M of the Earth, little m, over 2r, because it's not in orbit to start with. You can't use this. It's not in orbit. Don't fall into that trap. You can only use that for kinetic energy if it is in orbit. So we're still stuck with this. So we're going to go back to this right here. That's what we're going to use for kinetic energy. It's not in orbit yet. And then this is its gravitational potential energy on the surface of the Earth. And you notice that it does have speed. It does have kinetic energy because the Earth is turning very fast. And so that's its kinetic energy when it's on the surface of the Earth. It does have some because the Earth is spinning. Its gravitational potential energy on the surface of the Earth. Notice that is the radius of the Earth right there. We neglect the radius of the satellite because it's so tiny. And then this is how much work we have to do. So that'll tell us how much fuel we have to add to our rocket to get it up there. And this is the total energy once it is in orbit. That is going to be its total energy. So all we need to do is solve this for work non-conservative, and we are there. We figured out how much energy we have to add. A few other tricks, you're going to derive this for part of a problem, but V, how can you get that? Well, notice, so I'll just give you this one hint, how to get V at the equator. Well, how far is it moving in how much time? To get V at the equator, V equals, it goes around the Earth 2 pi r of the Earth, and it takes how long to do that? That takes 24 hours. And I'll have to convert that to, this will have to be converted to seconds, but that'll give you how far it goes in one day. Convert that to seconds, and you've got the speed at the equator. It's about 1,000 miles an hour, about approximately 500 meters per second. That's very approximate, but that actually gives us a major head start, which is why we always launch satellites from the equator or as close as we can get, like Florida or Texas. Cool. So that is how we can determine how much work we have to do to get a satellite in orbit.